Hello, and welcome back to the last part of Chapter 6. So just in review of hypothesis testing, the steps that you want to go through is you want to develop your null and alternative hypothesis. Typically, you want to prove your alternative hypothesis, so you need to state the null in such a way that it can be rejected if that's what you find. You need to then, the second step is to specify the level of significance. That is, that you do not want to make a type 1 error. Typically, it's going to be either 5% or 1%. And then you need to determine whether you're going to do a one-tail or two-tail test. Then step 3, collect the data and compute the value of your test statistic. And then step 4, use that value of the test statistic to compute the p-value. And then always reject your null hypothesis if the p-value is less than your alpha or your level of significance. And then the last step here, interpret the statistical conclusion in the context of the application. The next thing we want to discuss is how to create a confidence interval so that you're confident that whatever your test statistic is within that interval, and that there's only a small probability that it lies outside of that interval. So here we have a two-tail test. The null hypothesis is the mean is equal to the sample mean of whatever you're looking at, or the alternative that it's not equal to. So first of all, you select a random sample from the population and use the value of that sample mean to develop that confidence interval about for the population mean. So here's our sample mean, and then it's going to be a t statistic with your alpha divided by 2. Remember, it's going to be on each tail of your probably normal distribution, and then your variance divided by the square root of n. Right? If the confidence interval contains the hypothesized value, this one, do not reject your null hypothesis, otherwise reject the null hypothesis. And so we've seen this slide before, and so here we have one tail test and another tail test, and then the two-tailed test. So this is the lower tail test, this is the upper tail test, and this is the two-tail test when they're equal. And you could think of this as the upper is that when the alternative, when the population proportion is going to be bigger than the sample. Same here, it's less than for your alternative. That's one way to identify if it's a lower tail or upper tail. So here we're doing this population proportion, and we can calculate the z statistic. Remember, z was just a standardized deviation from around the mean, and if it was greater than 3, then it was an outlier. So we calculate this z, and then from that we get a p-value. So the p-value is the probability that z is greater than whatever alpha divided by 2 is. So in this case, 2.5%, I believe. So we're following along with the problem in the book starting on page 265, and this is about the Pine Creek golf course. And so we're interested in knowing if the proportion of women players is greater than 20%. That's what we think the alternative is. The null hypothesis is that it's staying the same or it's less. So this example takes you through exactly how you would do the calculation and do the test. So we want to know the sample size as a count. There's 400. The response of interest for females, it's going to be female, so we're going to do a count if in this range of our sample, and it's equal to D4, which is female. So there's 100 female that responded. the sample proportion of female then is 100 divided by 400, which is 0.25. That's what this calculation is. We believe that the null value is 20%. So that's where the 0.2 came from. We calculate the standard error, and then we calculate the test statistic Z, that's 2.5. So that's not equal to the alpha divided by 0.5 or divided by 2. So then we calculate our p-value for the lower tail, and we can use our function norm.s distributed, so it's a sample. Then we're going to use D11, which is our test statistic, and we want it to be true. And then our upper tail then is 1 minus that, so we have somewhere between 0.0062 and 0.9938 is where the p-values would lie. And then the p-value for a two-tail is 2 times the minimum of these, which is 0.0124. So it's the exact same logic as we did as the test statistic, but now we're just looking at a population proportion. So just keep in mind that we reject the null hypothesis when the p-value, in this case we're doing an upper tail, is less than alpha. So for alpha is 0.05, then it's 0.0062 is less than that, we would reject. So the summary then of these hypothesis tests. So here's our hypothesis, the type of test it is, the test statistic is Z, and how we calculate that, and then how we get the p-value. And so you'll notice we use that normal sample distribution function. We put in our Z value here and true, and then we can do 2 times the min of whatever this value is here for the two-tail test. Alright, so hopefully that's easy enough just to plug in and get those values when you're doing population proportion testing. The next thing we want to talk about is big data, statistical inference, and practical significance. So when you're doing your testing, you need to think about something called sampling error. And that's deviation from the sample from the population. And that deviation is called sampling error. And it happens because you're doing the random sampling. So no random sample is going to be quite exactly what the population is. And so if you're off by a lot, sometimes that can be attributed to your sampling error. So you want to try and think about your sample. Is it truly random? Are you throwing in any bias? And so on. If you have any other type of error that's not sampling error, then it's going to be referred to as non-sampling error. Some other types of errors you can have are called coverage error. And this happens when whatever you're looking at, your research objectives and the population from where you're drawing your random sample are not aligned. So you're not covering the right type of area to draw that sample from that really maps to your population. Another type of error is called non-response error. And this happens when you were drawing from a population, a sample population, and segments of that target population are either underrepresented or overrepresented in your sample. So you're getting whoever you're not collecting from, that's the non-response error. And then lastly on this slide, you can have something called a measurement error. And that's where you're having an incorrect measurement of whatever you're trying to measure. So how do you avoid non-sampling errors? First of all, you need to really define your target population, right? Then design the data collection process, and then train the data collectors on how to collect the data so that it'll be the same on every time that you're taking a sample. Sometimes you may want to pre-test the data collection to identify potential sources of error. So I would also recommend doing this if you're doing any kind of initial type of research that hasn't been done before, and you get responses back and you're going, oh, I wish I would have asked this or collected this additional information. So you typically would do a pilot study first, so that if there are areas like this, then in your larger study you could incorporate that in, and then you'll have the data that you're looking for. You also want to use a stratified random sample when the population level information is important qualitative variable. You would also want to do some cluster sampling when your population can be divided into heterogeneous subgroups or clusters. So maybe you're looking at age groups and you need to know a certain amount of people in each range of ages. So you want to divide that in so that maybe later on you're going to do some kind of comparison between the different age groups. And that also relates to the last bullet point here, is that use a systematic sampling when the population level information is about an important quantitative variable. And just know that you're going to get some kind of sampling error in your sample. The thing is that you need to try and control for those errors. If you were to present your research, somebody's going to ask you how you controlled, and if you didn't control, then your outcomes are going to be less credible. So next, let's talk about big data. And so big data is more than just, having a couple of 100,000 rows in a spreadsheet. We're now collecting huge amounts of data. As you can see here, estimates say that maybe 2.5 quintillion bytes of data are created every day. And, just think about how much data that is and how much it's being collected and stored, but nobody knows exactly what to do with it. And so because we have all these big data sets, then using the current methodologies that we have, they're just not adequate for analyzing this data. And so that's what we mean by big data. Some places where we get big data is anytime we do sensors. I think one time I read last couple of years that the jet engines on planes now have enough sensors in them that on a typical flight they will collect about 2 gigabytes worth of data. And so, just to analyze that one flight may not have enough statistical means to process that large amount of data. To put that into memory and to start trying to manipulate it with the type of statistics that we've been using, your machine would probably just bog down and would take hours in order to get done. Some other places where big data comes from is any kind of internet activities. I know the school here collects all the data anytime somebody signs in, what web pages they visit, and so on, so they can see where the visitors are coming from, what pages they landed on, how long they spent, where did they go next, what kind of search did they do in order to arrive here, or if it was an organic landing, and so on. And so the terminology, from a long time ago, maybe a megabyte of data was huge. Then it went to gigabyte, then terabyte, and then petabyte became sort of a norm for large amounts of data. And so now we're now approaching something called a yottabyte, and that is 1,000 to the 8th. And so you can see this terminology for describing the size of big data sets on page 271 in your book. And it would look like this. And so you can see here we're thinking, okay, gigabytes are, a million megabytes. So you keep going up by that amount each time. You can see how large we're getting. We don't have PCs that have enough processing capability to take a data set like this and be able to manipulate it. So we have to do other things that's going to help us interpret that data and analyze it. So something we've seen from the first chapter, again, we have these 4 V's. So volume, the amount of data that's being generated; variety, the diversity in types and structure of data generated. So it could be numeric, it could be quantitative, it could be audio, it could be video. Those are different types of data, and now we need to have some way to analyze it. We look at the veracity or the reliability of the data generated, and then the velocity, how fast is it coming? So with that jet engine I was speaking about, that's coming almost immediately with those sensors. So if we're doing a lot of sensor data and we need to analyze something in real time, how do we do that? Also, when we talk about big data, you can think about tall data. And tall data means it's a data set that has so many observations that a traditional statistics inference has little meaning. So that we've seen as the number of observations go up, that what it has an impact on the distribution. So in the case of a lot of observations, just about everything becomes significant. But is that really telling us anything? We can also have something called wide data. Wide data means there's so many variables, and not typically, but for the most part, every variable has its own column. So if you think about adding more variables, that just makes it wider. So that's one way to think about wide data. Tall data means it's like a long spreadsheet. You just keep adding more and more rows or more observations. So looking at some calculations that are in your book, we see that in table 610, and I'll show that shortly, shows how the standard error of a sampling distribution of the sample mean time spent by individual customers when they visit this PDT website. That sampling error decreases as the sample size increases. The 6.1 table shows how that standard error of the sampling distribution of the proportion of the sample that clicked on any of the ads featured on the PDT or Pennington Daily Times decreases as the sample size increases. And so what we're showing is that with big data, the standard error where n is a billion is 1/10,000th of the standard error when n is 10. So as we collect more and more data, that standard error gets smaller and smaller. So then everything becomes significant. Right. So here you see the sample proportions, the same sort of result. We have a different calculation for our standard error, but you can see how when it gets to this side, it's very, very small, and again, makes everything significant. So the next thing I want to talk about is how does big data impact on confidence intervals. So confidence intervals, are great tools for making inferences about your population parameters. But how valid are they when it gets to large data sets and what's happening when the data sets are very huge. And so those intervals estimates depend on the quality data that you use to develop those interval estimates. So the intervals for population mean and population proportions become narrow as the size of the sample increases. So there's less and less chance that it's going to be there. And so that potential sampling error also decreases as the sample size increases. So we're more likely to have a good, I guess you would think, sample that represents the population. And so if we look at the next two tables, they show us the confidence level and the margins of error decreases as the sample sizes increases. So this is for the population mean. You can see this margin of error. Right, so the T alpha divided by 2. So when we get to 1,000,000, then that margin of error gets very, very small. And again, everything is going to be less than alpha here when we start to do our statistics and significance. When we look at the proportions, you see that it gets, after 1,000, it gets very, very small again, that margin of error. So some implications for big data for confidence interval. All right, so there's 3 possible reasons that a sample mean differs from the population mean. There's sampling error, which we've discussed, non-sampling error, and either the population mean has changed since last year. So we're looking at this PDT example from a big data perspective. So if you've read the chapter, we're looking at how long somebody is spending on the site. So we're looking at, okay, is it 0.1 seconds more each from last year or not? And so the implications on this interval, right? So if it's reliable evidence and that population mean has actually changed since last year, you still have to think about the impact on the difference between the sample mean you got this year and the mean from last year. So for example, if there is a 0.1 second difference, then there's a consequential effect on what that newspaper can charge for advertising on its site, because now people are spending more time. But it's not all that much time. So that's what it means. Otherwise, there's no practical significance of that 0.1 second difference. Maybe it doesn't mean anything. So what are the implications for confidence intervals? They're very useful when they're applied correctly. But like we've said, when you have those estimates, they become increasingly precise as the sample size increases. So if it's very large sample size, then you'll have extremely precise estimates. And you also need to keep in mind that no interval estimate, no matter how precise, will reflect the parameter being estimated unless you're assured that that sample is relatively free from sampling error. And that's going to be hard to do. And if you're going to do interval estimation, make sure you always consider whether that random sample of the population of interest has been taken. Does it contain everything that you really want to generalize to that population? So just as what I've been saying before, when we look at those standard errors, they get smaller and smaller, right, as the sample size increases. When that sample size is huge, any difference between your sample mean and the hypothesized population mean will result in a rejection of that null hypothesis. We'll look at the next two tables and see the p-value associated with a given difference between a point estimate and the hypothesized value of that parameter decreases as the sample size increases, which is the same thing as I've been saying before. Everything becomes significant, and you typically reject the null hypothesis. So here we're looking at the null hypothesis that we think the mean is less than or equal to 84. The sample mean is 84.1 seconds for the various sample sizes. So if we have a sample size of 10, the t-statistic is this, and the p-value is this. And you see that at about 100,000, then everything becomes significant. We would reject this value, saying that they are different. Even if it's only 0.1 difference. Here we have the table for a proportion, not a mean, and we can see 10,000. That becomes significant. That p-value will be less than or alpha if it's 0.05. And again, it's just 1/100th difference. So the implications then for big data and hypothesis testing is that the results of the hypothesis test, no matter what the sample size, is only reliable if the sample is relatively free from non-sampling error. If you do have non-sampling error in your data collection process, then you have a higher likelihood of making a type 1 or type 2 error. And when you do your hypothesis testing, you need to think carefully about whether your random sample of the population of interest has been taken. Is it going to generalize to the overall population? Did you get enough representative of that? And lastly, something to really keep in mind is that no business decision should be based solely on statistical inference. You need to be practical about it. Practical significance should always be considered along with your statistical significance. Think about what this is saying. Are you just showing it significant because it's so large? You may be making an error in your judgment because of that. And so that ends Chapter 6 on statistical inference. And next time we'll talk about Chapter 7, which is regression.